Hi everyone. Today we have Jaiver Magan giving us a talk on A Tale of Two Hungarians, Tridiagonalizing Random Matrices. Please.
Okay, thank you. Thank you for the invitation to speak at your seminar series, and also thank you for moving the seminar from yesterday to today. It was, apologies for the inconvenience. So today I want to describe a couple of works, one in collaboration with Vijay Balasubramanian, Pavel Kaputa, and Kinke Wu, aka Austin, and the other with Vijay and Austin. These works deal with a new measure of quantum state complexity, its relation to quantum chaos and black hole physics, and also how this measure suggests a different approach to chaos and random matrices. In a way, and I hope, I will make sense of the title at the end of the talk. In a way, these works combine the legacies of two Hungarians, namely Eugene Wigner, who is the father of random matrix theory, and Cornelius Lanczos, who is famous for his method of diagonalizing matrices based on tridiagonalization, which we are going to review in a few minutes. So, so let me start with the motivations for this work, and in particular with the ones coming from quantum complexity. In this context, there is always a huge problem already at the beginning regarding the definition of complexity itself. Some of the most famous definitions, such as Kolmogorov's, Risanen, and Nielsen, are all based on the fundamental idea that the complexity of an object should be understood as the number of simple components which are required to assemble it. As such, we faced an ambiguity already at this point. The measure of complexity depends completely on the basis of simple components. In the context of holography and quantum gravity, this ambiguity has appeared explicitly in several recent works that deal with Nielsen complexity and the associated penalties. And in this work, in regards to these motivations, we would like to somehow get rid of these ambiguities, and we will propose a potential way out. A different set of motivations come from the field of quantum chaos. So in this vein, random matrix theory, originally conceived by Wigner to understand the atomic nuclei, has been mainly used to understand the statistics of energy levels in chaotic theories. But here we are motivated to further understand the implication of this proposal, of this approach, in time-dependent scenarios. Relatedly, there is we will review it in a moment, but there is a famous conjecture in quantum chaos that states affirms the universality of spectral statistics in chaotic theories. This is the Boigas-Iannoni-Smith conjecture, and let me say that well, this is a very well studied conjecture, and it is well known that several aspects of this conjecture are encoded in the so-called spectral form factor of the theory, which we will define later. And this has been not only studied in the field of quantum chaos, but also in the context of black holes. With respect to these motivations, we will want to find, or we will seek to find the relation between this famous quantum chaology and quantum complexity. A different motivation, also related to chaos, comes from deepening the geometric approach to chaos and complexity developed recently in collaboration with Kaputa and Patramanis, Although we will not touch this today, please, we can talk later, or let me know if someone is interested through mail. Okay, so let's go to the last set of motivations that come from the field of quantum gravity. And here we are interested in the conjecture long-time complexity dynamics for chaotic systems and black holes, and also in the so-called holographic complexity proposals, such as the black hole interior volumes or the momentum complexity correspondence. With respect to these motivations, today we will mainly concentrate on the long-time dynamics of complexity. And indeed, we will refine such kinds of conjecture on such behavior. But we will see, I hope it will be clear by the end of the talk, that our complexity measure will turn out to be related to precise geometric avatars, so without any conjecture. And we hope that this will pave the way towards understanding the other points or conjectures as well. Okay, so if there are some talks about the motivation, please go ahead. Not I will continue with the plan of the talk. Okay, so having laid out the motivations, let me describe this plan. We will start with the definition of this complexity measure, and we will see how this proposal, this definition, connects with the Lanczos approach to matrix diagonalization. Then, following Wigner, and since we are interested in understanding aspects of chaotic systems, we will study this new measure in quantum chaotic theories by considering random matrix theory. We, in this context, we will particularly concentrate, although we have studied basically all times, but here in the talk, we will particularly concentrate on the long-time behavior of different physical scenarios. In the third part, to understand, well, and this will be done numerically. These were the first calculations that we did. But to understand this new, we will find new features, and to understand these new features analytically, we will see that the first step is to develop a new approach to random matrix theory, which is based on matrix tridiagonalization, and this will be discussed in the third part. We will end up with some discussion and summary. So, okay, let's move to the definition. So suppose we start with an initial state, such as this one here, and allow it to spread through time evolution. Basically, we have this expression here in terms of some basis, Bn. And in this spread, in this time evolution, the amount of spread of the wave function is definitely a sensible notion of complexity, but since it's going to be central in the following, let me characterize it a little bit more precisely. So consider an arbitrary order basis B. So any basis that you like, call it B. Let's put an order to it with this level n that goes from 0 to the dimension of the Hilbert space. And given this input, we can define more precisely the notion of a spread by this formula here. So in this formula, the coefficients Cn are strictly growing functions of n, and therefore, as the wave function spreads through the basis, this quantity grows accordingly. For example, we will use typically Cn equal to n, and with the choice, basically, this notion of complexity, this notion of a spread, counts the number of basis basis vectors that have been explored through the time evolution. An alternative measure of this spread is the exponential of the entropy of the probability distribution in the given basis. That this does not depend on the order of the basis. It still depends strongly on the choice of basis. And now, of course, the question that you might be thinking about is that, well, who chooses this basis? There is obviously a huge ambiguity regarding the choice of the basis, and this is very similar to the ambiguity. So we wanted to get rid of before, and indeed it is interesting to notice that many recent notions of complexity that have appeared in the literature. I mean, that the ones that have appeared in the literature for physics applications in quantum gravity can be written as the spread of as this in an abstract way as this notion of a spread for certain different choices of basis. This was explained in this paper here. So what we propose in this work is that in Kolmogorov's spirit, complexity should be defined as the minimum choice, as the minimum overall the possible ambiguities. In this case, overall the choices of basis and overall the choices of order per basis. Now, typically these minimizations are not doable in practice.
Question.
Yep.
Sorry, Javier. Sorry, I have a question. Can you go back to the previous slide?
Yeah.
So this is this looks like, so you take your state and you perform a measurement in some basis, right? And then you're calculating the Shannon entropy of the probabilities that you read off, right? That's what this SBT is, right? So is there something you're saying then minimize this over all choices of basis? So it's a minimum of Shannon entropy over all course of all sorts of measurements you can perform. I thought that was related to one entropy of another way, one way or another.
Well, it is related. I mean, it is trivially related to the von Neumann entropy of the project of the algebra. I mean, if I define the algebra of projectors in a given basis, which is the algebra of the Bn ket Bn bra, no, for all the bases, this is a classical algebra. Is the diagonal algebra for that basis. Well, the von Neumann entropy, the entanglement entropy of that algebra, the von Neumann entropy of that algebra is this function here, yes, as you are saying. And but the intuition is that it counts the number of it counts the support of the wave function in that basis, the amount, I mean, the size of the support. Actually, if you have heard about this, for example, operator growth and the notion of size. The notion of size is just the same thing as this for a given choice of basis, say the computational basis.
Sorry, but I can always choose my state as one element of the basis, and then this entropy is 0.
Yeah, very good. Can I? Yeah, that will be the next slide. But just wait 1 minute. Okay. Did I answer the question, Nima?
Yeah, basically, but the question is exactly what Martin is asking as well, because like the state is pure, therefore its von Neumann entropy is 0, which means that the minimum over all these entropies is achieved as 0. And how do you achieve it? You just pick one of the BNs to be equal to psi t, and then you get
exactly. But we want to choose. Okay. Yeah. Let me then go to the next basis, the next slide. Okay. So let's discuss that. So. Of course, we cannot. I mean, that cannot be the minimization that we want to do. That will be a minimization per different times. At each time, I choose a different basis. Okay. I don't want to do that minimization. I want to choose one basis once and for all, and I want to do certain functional minimization that ensures that the complexity is going to be a minimum as time evolves. but I'm not allowed to choose. The game is that I'm not allowed to choose to change the basis at each time. Notice that if I, for example, choose, I mean, your proposal would be to choose, for example, psi 0 at time 0, psi, let's say t, or some at t1, and those typically are not orthonormal. So you are choosing completely different orthonormal bases at each time, and the point is that you want to choose to compare different bases in a finite extension of time. Okay, so this is going to be a functional minimization. It's not a minimization per instantaneous time event.
Yeah, maybe when you write an expression for it explicitly, will become clearer. Thank you.
Yeah. Yeah. So what we So let me before entering in the minimization, let me say that well, at least as with the rules that we propose, that I'm going to explain in a moment, this minimization can be carried out in practice. And before stating the result, let me say that given an initial state and a unitary evolution, okay, so the one like the one we were considered before, there is a canonical basis that we can construct out of it. Basically, we compute the action of the different powers of the Hamiltonian in the initial state. So we compute all these vectors here. Okay, these vectors are not normalized, neither normalized nor orthogonal between each other. But we can take these vectors and use the Gram-Schmidt orthogonalization procedure, and this gives rise to an orthonormal basis for the part of the Hilbert space that is explored by the time evolution. This basis is sometimes called the Kirchhoff basis in the condensed matter literature, and now in the higher energy literature as well. So let me explain what do we minimize before for the discrete time scenario, which is easier to explain. Okay, so what we minimize is that we do a minimization. I mean, there might be other definitions of this functional minimization, but it has to be a functional minimization over a finite amount of time extent. So we say that first we are at time 0, we want to minimize at time 0. Then we take that state. Okay, that state is already part of the basis. Now I cannot. The game is that I cannot. In the next step, I cannot choose it not to be part of the basis. Okay. Then in the next step, I need to minimize again the notion of a spread given the first state that is already in the basis, and so on and so forth. This is the constraint that allows me to compare consistently given choices of basis for all times. Well, this is one possibility. It is understood. Basically,
yes.
Basically, so let me explain this formula here. So basically, we have in the discrete time scenario, the continuous time is a little bit more difficult to explain here on Zoom, but it is basically the same. But let's say that I start with psi 0, as you guys have said, the best choice is to choose psi 0, okay? Because then the complexity, I mean, the minimum is 0. So that's good because we still didn't evolve the state. So the complexity produced is 0. Now we evolve the state in a discrete time scenario. This would provide a different psi 1, okay? And I want to choose the basis that minimize the spread or at initial time and at the second time. So if I choose the psi 1, I would minimize the complexity at that time, but I would destroy the minimization at the first time, okay? And I want to minimize as time evolves, okay? So in this case, to minimize the complexity, what I should do is, the spread, what I should do is first to take these vectors I want, to find the projection into the first vector, no, psi 0, and then therefore to compute the perpendicular support, the perpendicular to psi 0. Now I notice that I didn't draw it very perpendicularly, but this should be perpendicular to this one. And then this vector, the perpendicular support, I choose it as part of the basis, and one can convince, you can convince what is explained better in the article, but apply the formula, this basis, this choice of basis would be the one that minimizes overall possible choices. You could have chosen any other basis for the first 2 times, and so on and so forth.
But you minimize the sum? No, because here I could do two different linear combinations that might reduce the entropy, right? Or so you minimize the sum of the entropy at 0 plus the entropy at 1, or?
No, I minimize first at 0, there and 1. So I do like what is called lexicographic minimization.
Okay.
So okay, yeah. So the functional minimization, it's if you want the technical word, it's as a lexicographic minimization. For every basis, I construct let's say a string in which I have all the complexities, and I define one basis to be worse than the other if I compare two bases step by step, okay? And if one basis is worse than the other at a previous time, then that I define to be worst, even if maybe at later times it is better.
Okay.
Okay, so these rules are, I agree, are somewhat arbitrary. I hope that the results, which are the important things, the applications to physics that I will present, will convince that they are nice to consider. But still, I completely sympathize to the fact that there might be other notions of functional minimizations for these notions of a spread, and we have spent some time thinking about those. We still didn't arrive to any consistent proposals, but it is clear that it has to be something in this line of functional minimization, in which you choose a given basis and compute something that has to do with the full evolution in time, and compare bases in that way. So the minimization in the continuous case is basically this lexicographic minimization with the derivatives of complexity or the derivatives of entropy. So we construct these strings in which we compute basically the derivatives of the entropy with respect to time, and the n derivative of the entropy with respect to time at time equal to 0, and we compare different bases, and we prove that basically these Kirchhoff bases, both at the continuous for the continuous time and for the discrete time, are the ones that minimize that notion of functional minimization. It is understood. Maybe we can discuss this. I don't want to seem that this is completely clear. It's just a very arbitrary proposal that we have done, and maybe we can discuss whether it is good or bad at the end, but I prefer to continue with the implications of this proposal. So the output of these theorems, that although they, as we have said, they start from certain arbitrary set of rules, but otherwise they are not simple to prove. is that to compute the previous notion of spread complexity, we must derive this kernel of basis. So let me repeat with what is this kernel of basis for the people that are not used to it. So by this, we mean that we start with the vectors that appear by repeated action of the Hamiltonian in the initial state. So these vectors here, okay? And then with those vectors, which are neither normalized nor orthogonal, we perform Gram-Schmidt orthogonalization and derive the orthonormal basis, these Kns, for the subspace of the Hilbert space that is explored by the time evolution. This problem, let me say that this problem is well known in the literature. The solution is also well known and comes under the name of the Lanczos algorithm, developed by one of the Hungarians, Cornelius Lanczos, and a nice book on the subject is this reference here. So basically, the Lanczos algorithm is expressed by these two simple equations here, which instruct us how to get the n+1 Kirillov basis vector out of the previous ones. Basically, this n+1, then we are going to normalize it, and we obtain it from the previous Kn and Kn -1. In these equations, these coefficients, the Ans and the Bns, are known as the Lanczos coefficients, and we and they are derived also in the iterative process, one at a time. So it is simple. I mean, one just needs to invert basically this equation, but it is very simple to see that given this iterative process, the Hamiltonian in the Kirillov basis, so I just apply the Hamiltonian now to the Kn, acts in this very simple way. It is basically a tridiagonal matrix of this sort. So we have the Lanczos coefficients here, and zeros here, and zeros here. So the first step in this game, in this proposal, is thus to tridiagonalize the matrix. Okay, so finding this form of the Hamiltonian. For finite dimensional matrices, this form of the Hamiltonian, or this form of a matrix, is called the Hessenberg form. And there are numerically stable algorithms for computing this Hessenberg form. Even Mathematica has such a subroutine.
Sorry, can I ask a basic question?
Yeah.
What is vector An? How do you get A0? Vector A0?
Yeah, A0. Yeah. Okay. Let me one moment. So so psi 0 is K0. Okay. So yeah. I already, so these are the initial conditions of the iterative process. Okay. So psi 0 is K0. Now I don't need, there is no A0. Okay. Because I go to A1. What is A1? Well, it's H times K0, basically.
Okay, I see.
And then I normalize. Basically, the A's are the K's. Basically, they are just not normalized. Okay.
Okay.
Is the relation here?
I see. Thank you very much.
So for finite systems with discrete spectra, such as, for example, the Sazdev G-Iterative model or matrix models, we can use these subroutines that compute the Hessenberg form and read off directly the Lanczos coefficients from them. There is another method that also works for infinite dimensional systems, or even systems with continuous spectrum. We developed that in the article. The starting point is the so-called survival amplitude, which is by definition the amplitude for the state to remain unchanged. So is this quantity here? And from this article, we explain in the article how to obtain the Lanczos coefficients and therefore find the tridiagonal version of the Hamiltonian. And it is highly sophisticated. I mean, it's kind of sophisticated and complicated, and we are not going to use this method in this talk. So I will not review it, but it's important conceptually that all this notion of spread complexity and the Lanczos algorithm and everything that I'm going to say could be derived directly from this quantity here, from the survival amplitude. Okay, so using any of these methods, once we have the Lanczos coefficients, we proceed as follows. So we expand the time evolving state on the kilo basis. On this basis, the Schrödinger equation takes this explicit form here. It is just the same equation as the tridiagonal version that I was writing before. And here the survival amplitude, it is just, notice that it is just the first amplitude in the kilo basis. And from this amplitude, from this first amplitude and the Lanczos coefficients, we can derive all the wave function algebraically. So actually, in numerical computations, we do something even simpler. Basically, we just find the Lanczos coefficients. Therefore, we have the Hamiltonian in this tridiagonal form. We matrix exponentiate it and apply it to the initial state, and then we just rid of the amplitudes. And then, of course, once we have all the amplitudes, all the science, we can compute the probabilities, and from those we can compute these two notions of complexity defined earlier. So this is admittedly a somewhat involved computational process, but the interesting point is that let me remark again, it is otherwise straightforward. Okay, so this is a computable notion of complexity. In a way, since it's computable, it is not really a true notion of quantum circuit complexity, but still it will have very interesting applications, as now I'm going to describe. So before moving on to specific examples and to motivate that this is a worldwide direction, it is illuminated just to apply this framework to the thermofieldable state. So the thermofieldable state is defined as usual. So we basically make the tensor product of the original Hilbert space with itself. Okay, we call one of the theories the left and the other the right, and we then use the eigenstates of the original Hamiltonian to construct this state here. Okay. So these ends are the eigenstates of the left and the right, and these amplitudes are the amplitudes of each state. And this state is basically constructed so as to purify the thermal ensemble of each of the left and right theories. Now, this state is invariant under evolution generated by the difference of left and right Hamiltonians, but it is not invariant under evolution with, say, only one Hamiltonian. Under evolution with only one Hamiltonian, such as this, or with the sum of the Hamiltonians, which is equivalent, one obtains an analytically continuous thermofield level. So basically, one obtains phases here, and they can be encoded by saying that we analytically continue the temperature. In the context of ADS-CFT, famously, thermofield levels are dual to eternal black holes, and this evolution, although this is not clear, but this evolution is expected to describe aspects of the black hole interior. Okay, what is important for us is that so this is well known, but what is important for us is that the survival amplitude for this time evolution is just the analytically continuous partition function. Okay, so in other words, the survival probability is what is known in the quantum chaos, in the field of quantum chaos, is what is known as the spectral form factor of the theory. So remember that I said that everything, I mean, this notion of complexity and all this wave function in the kilo basis and basically everything what we are going to deal is dependent. I mean, is fully is a complicated functional of this survival amplitude, which in this case is just the spectral form factor. So we are going to see a precise relation between this notion of complexity and this famous quantities studied in the field of quantum chaos. So let me say that. Let me explain a little bit more. This spectral form factor, that is the modulus of this survival amplitude, the modulus of the survival amplitude square, has played a leading role in the context of quantum chaos by basically codifying, between other things, the universality of spectral statistics, and also codifying the differences between, as we are going to see, between different universality classes. And but it has also played an important role in recent research in the context of quantum black holes. But what is important here is that it is seen as the first entry. So instead of just an abstract quantity that one can compute that contains information about the spectrum, here it is seen as just the first entry of a huge probability distribution, which is the probability distribution in the Kirillov basis of this dynamical time evolution. So this is, I mean, I hope it is clear that this is a very promising avenue to build the bridge between the quantum complexity, quantum chaos, and quantum gravity. And I just have one moment to see if there are questions about this.
I have a sort of philosophical question. So you are using this as an example of a state, but obviously this is related to the density matrix of a thermal system. So are you also trying to assign complexity to the density matrix and think that this S of t?
No, I'm saying that so this notion of spread complexity is a notion of complexity associated with time evolution and an initial state, okay? And just to motivate it, I'm saying that, for example, in the context of quantum black holes, one time evolution that is expected to be important and that is expected to teach us some things about the interior of the black hole is the time evolution of the thermofield level with only one Hamiltonian, let's say the left, or with the sum of both, okay? This evolution, as you are saying, I mean, well, I don't know if you are saying this, but this evolution actually doesn't change the reduced density metrics. The reduced density metrics are always thermal, okay? And the entropy, the black hole entropy is always the thermal entropy. But the evolution changed the state a lot. And with this quantity, we are approaching. I mean, we are basically studying this change in the state. Okay. What I'm saying is that the notion of complexity that we are proposing is just dependent on the survival amplitude. And in this case,
but I think you were going to take. I don't know if I understood correctly because you didn't. But this S of t, you're going to take, for example, derivatives at t equals 0. That would be one way.
Yeah. Well,
wouldn't those be like expectation values in the thermal
of the Hamiltonian? Yeah, this is another. Yeah, this I didn't explain. Okay, yeah, well, good comment. So before I said that this survival amplitude in general, it's enough to derive basically the Lanczos coefficients and derive everything in this game. I didn't explain the path in which that is done, but actually the path is exactly what you're saying. You take derivatives like n derivatives with a general n of this S of t, and that brings down powers of the Hamiltonian. So basically you compute moments of the Hamiltonian in the initial state, okay? And with that is enough to compute all these quantities. Okay, so in this case, in the case of the thermofield double, doing that would be to compute powers of the Hamiltonian. I mean, the thermal expectation value of powers of the Hamiltonian, of infinite, of arbitrary powers of the Hamiltonian.
So what your quantity has some interpretation of something in the thermal state, I guess.
Exactly. Or something dynamical about the thermal state. It's not just the thermal. It connects the static properties with dynamical properties. Yes.
Okay.
That's what I'm trying to say with this slide. That is nice that this proposal explicitly relates something dynamical, like the evolution of the black hole wave function, the survival amplitude, and the complexity, with something that is non-dynamical, like the statistics of the Hamiltonian in the thermal ensemble. So that's the kind of that was the motivation for us to choose this measure.
Okay, thank you.
So,
sorry, can I ask
yeah.
a question?
Yeah.
So this is a naive question, but so it's about like density matrix, what Martin mentioned, but so in this framework, you have defined the complexity measure for the unitary time evolution. But can you do it for a non-unitary time evolution for like the quantum channel by introducing the ancilla to purify it? And
if you introduce the ancilla to purify it, yes. If you don't, I'm not sure that there is a unique way. I mean, probably there are. Yeah, but that is it's a good question, and it's undone. I mean, so but yeah, for sure, if you have one way, you have a density matrix, you can purify it, and then you can evolve one of them, and this basically is the same thing as I'm saying here, just for other notion of thermofield level with other notion of modular Hamiltonian, but it's the same thing.
Okay, I see. Thank you.
Okay, so let me mention that there are interesting examples that are controlled by symmetry, in which all these involved process can be followed in a fully analytic manner. These examples actually include, they were studied in this paper, and they include models related to 2D gravity and models related to 2D conformal field theories, which basically are controlled from this perspective by the SL2R group. And well, I won't describe them here, but these are good toy models to that actually have implications in which all these can be followed in full detail. So okay, but for the sake of time, let's directly apply these ideas to the more interesting case of random matrix theory. So before describing the explicit results, let me motivate a bit these models and why and where we should trust their predictions. So first, a basic conjecture states that the fine-grained structure of the spectrum of a quantum chaotic Hamiltonian is well approximated by the statistics of random matrices. So this is sometimes known as the Boigas-Giannoni-Smith conjecture, and given this conjecture and also the energy time uncertainty principle, we expect that aspects of the long time dynamics in chaotic systems will be very well described by the statistics of nearby eigenvalues of the Hamiltonian in the random matrix approximation. Okay, so we are so therefore, since we seek to understand the universal aspects of black holes and more general chaotic systems, and in particular, we seek to understand their long time dynamics, it is natural to start by considering random Hamiltonians. Okay, so we are going to study all three universality classes: the Gaussian unitary ensemble, the Gaussian orthogonal ensemble, and the Gaussian symplectic ensemble. For the moment, numerically, and then we will later.
Quick question.
Yeah.
So when you say long time or you say small gaps, how long, how small, how small?
Exponential. It's exponential. See, to be sure, and for the present talk is enough. It's not exactly exponential. It's exponential in the entropy, and small is exponentially small in the entropy, but actually it's a little bit less. It's in random, in Gaussian random matrices is e to the s divided by 2.
But
it's a question that depends on the model. I just want to say that the question you are asking, when the random matrix behavior, the universality of random matrix behavior is good approximation, is a question that highly depends on the model under consideration. Okay.
But your intuition says that the random matrix behavior kicks in exponential long times, not in parallel times. Is that right?
Exponentially long. Yeah, it could be e to the s divided by 2, but exponentially long.
Yeah, but that's still exponentially long.
Yeah.
Okay, thank you.
But I'm saying that is highly dependent on the definition of the random matrix and also on the thing you want to study. So I wouldn't. I mean, just take that for a moment. But
sorry. What I'm asking is a little bit different. I'm asking, so e to minus alpha s is still exponentially s. The coefficient alpha could depend on the system, but I'm asking whether the exponential is a universal feature in all chaotic system, or is it, do you expect the onset of the random matrix model to be exponential long times? I don't care about the coefficient.
Yeah, well, it depends. I mean, for example, now if you include not only the random matrix approximation for the Hamiltonian, but you also put a random matrix approximation for operators in the vein of the Einstein thermalization hypothesis, then you can go to smaller times and you can get the intuition about thermalization and chaotic dynamics using just Einstein thermalization hypothesis and go to smaller times. So what I'm saying is it depends on a lot of things. I don't want to. We can. This is not about my talk. We can discuss maybe that at the end of the talk. I'm just saying that is highly dependent on how you define your random matrix theory and your operators and your quantities that you're going to study. It is. I wouldn't say that there is nothing universal in that sense. It depends on several things. Yeah.
Okay.
Okay, so to start at some concrete point, let's choose the Gaussian unitary ensemble, which is defined as an ensemble of Hermitian n by n matrices with a Gaussian measure. Well, just to say one thing, for example, the spectra. I mean, just to be concrete with something. So, if you would ask me, okay, in random matrix theory, and you are computing the spectral form factor, then I would say that yes, it is. I expect it to be exponential. Okay, for that question, for example. But yeah, then other questions depends on other things. So given this ensemble of finite dimensional Hamiltonians, we are now going to follow these different steps. This set of steps for different values of n. So we first take. This is all numerical for the moment. We first take an instance of a random Hamiltonian. So we generate it with Mathematica, for example. We diagonalize it, and then we have a set of eigenvalues and a set of eigenvectors. And with those, we can construct explicitly the thermofilable state. We can also then evolve it in the way that we said, just with one side. So constructing this time-shifted thermofilable state. And then we can find the Hamiltonian in the kilo basis, which here, this tridiagonal Hamiltonian, which here can be done simply by putting it in the Heisenberg form, by using these subroutines that I was mentioning. And from such a form, we can read the Lanczos coefficients. Then we just exponentiate this form of the Hamiltonian and apply it to the initial state, and we can read the wave function. And then from the wave function, we can compute the quantum state complexity. We do this for different values of n and different repetitions, and then we plot the results, or we take the average, and as we are going to see. It is more or less clear the things we are going to compute. Okay, So let's start with the results for the Lanczos coefficient. So basically, as I said, we take a random a particular instance of a Hamiltonian drawn from this Gaussian unitary ensemble, and we construct the thermofilable state. We construct the Hamiltonian that actually evolves this thermofilable state on one side only, and then we tridiagonalize it and find these ANs, which are the diagonals, and the BNs, which are the off diagonals. Okay, and for finite n, for finite dimensions, these are given in these two figures here. The A's plateau very rapidly at 0, and the B's slowly decay with a rate of order. So here n is the Lanczos index, and the small n, and the big N is the dimension of the Hilbert space. Okay. So we see that the B's slowly decay with a rate which is order 1 over the dimension of the Hilbert space. So this is a non-perturbative effect, let's say, in gravity. The fact that they decay so slowly means that for any finite interval of little n, so let's say you want to explore BNs from little n 5 to little n 100, these B's are completely constant. But of course, they need to decay to 0 since the system is finite, and the Lanczos algorithm must halt when we have produced a full basis of the Hilbert space, which is the typical thing in chaotic systems. So let me say that, so basically what I'm saying is that these BNs, although they seem to be decaying, you should see them really as basically constant over very long patches of little n. Let me say that similar behavior has been found for the B's in the context of Kirchhoff complexity recently in this article. Okay, and let's now move so to the important part. So now, using these Lanczos coefficients, we can compute this wave function, we can compute the probabilities, and we can compute this spread complexity. And we do this in this figure here. Notice the complexity is normalized by the dimension of the Hilbert space, as well as the time is also normalized by the dimension of the Hilbert space. So everything that you see of order 1 here in this plot is actually of order the dimension of the Hilbert space. In this figure, the dark hues correspond to the Gaussian unitary ensemble for different temperatures. And quite interestingly, we conclude that the Gaussian unitary ensemble displays 4 regimes. We have a ramp for exponentially long times, a linear ramp, as Susskind conjecture, until a peak of exponential size, this peak here. Then a downward slope until a plateau is reached. The plateau time and height are exponential in the entropy as well. So so this verifies or is consistent with Susskind conjecture on the behavior of complexity, but it actually refines it because it shows this funny fact that the complexity actually grows a little bit more and then decays. Okay, everything, of course, in the of exponential size. So it's just a question of the prefactor. So notice that in this plot we also plot a related ensemble with light hues. Is this one here? This corresponds to picking eigenvalues from the Wigner semicircle law and running the program again. So basically, we don't take a random matrix, compute the eigenvalues, and then use those eigenvalues. We just take the Wigner semicircle law and draw eigenvalues from that. What that means is that that is a way of erasing the universality of random matrix theory. And we see qualitatively similar behavior, but the complexity dynamics miss the peak and the slope. And we are going to explain this in a moment. Before doing that, let me say that this behavior, maybe for some of you, reminds to the behavior of the spectral form factor in random matrix theory. So from the perspective, let me remind that the spectral form factor is just the first entry in this probability distribution in the kilo basis. And let me remind also that this spectral form factor typically shows 4 regimes as well: a slope, a dip, a ramp, and a plateau. In this case, it is known, like analytically, that the dip, this behavior, this fact that it goes beyond and then goes up, that the dip and slope are originated in the notion of spectral rigidity in the matrix model. This spectral rigidity are basically the universal correlations between the eigenvalues that are not so near to each other. And in this scenario, the ramp, this thing here, and spectral rigidity are related because they are basically a Fourier transform of each other. Okay, but in the complexity case, this slope here is a very subtle regime that is not directly related to spectral correlations, and to show that it's controlled by that, we need to make some arguments. So basically, the question is, how do we know that the complexity slope arises from spectral rigidity? One strong hint is, again, to consider another ensemble with the same density of states, but with no universal correlations. With this ensemble, the spectral form factor, so it is this here, the light, again, the light hue, okay? It is the spectral form factor shows no ramp, and the complexity shows no slope, okay? So basically what we are seeing is that when we erase universal correlations, we erase both the ramp in the spectral form factor and the slope in the complexity, and this is a strong argument that this is controlled by that this encodes universal statistics in the random matrix theory. We are going to see a further stronger argument in a moment. Before that, and to better understand the physics of the complexity slope and the long time behavior of the exact wave function, we can follow in time, take snapshots basically of the thermofield level probability distribution exactly. No? So this is done here for different times. Here the spectral form factor is just the entry 0, so it's just this entry 0, no, which decays very fast. But we see much more information in all of the other entries. We see that the wave function of the thermofield level behaves as a coherent subwave, leaving a relatively small, so it goes as a coherent subwave, leaving this small tail of probability behind. In particular, what is interesting is that the front of this subwave overshoots the plateau and bounce back at the end of the Hilbert space before it saturates, and this is the origin of this complexity slope. Okay, so to deepen more on the origin of this slope, let me notice something. It is well known in the literature of random matrices and quantum chaos that the spectral form factor differentiates between 3 universality classes: the Gaussian unitary ensemble, the Gaussian orthogonal ensemble, and the Gaussian symplectic ensemble. This is explained in this book here, from where I extracted this plot. Notice that the Gaussian unitary ensemble is this one here. It shows a sharp transition. The Gaussian orthogonal ensemble is this one here. It shows a smooth transition. And the Gaussian symplectic ensemble shows this weird pink kink here. So using the same methods, we can compute the complexity for the Gaussian orthogonal and the Gaussian symplectic, and which are shown here. This is the Gaussian orthogonal. This is the Gaussian symplectic, and we see that the complexity slope, the shape of the complexity slope, demonstrates the difference between universality classes, and provides a further argument that it is controlled by the same spectral rigidity that controls the ramp in the spectral form factor. Finally, Finally, let me say that one could be critical and say that this only holds for random matrices and not for realistic black hole models or realistic quantum chaotic models. And to show that this is not the case, in the article, we repeated the calculations for the J-K-type model, which is a realistic model of quantum black holes, at least in low dimensions, and obtained qualitatively similar results. Is there some questions here?
I didn't, not in just, I don't know, technical. So these results depend only on the spectrum. So
Yes.
if you know the eigen, so you don't need to do the Lanczos. You need to find the eigenvectors, eigenvalues of the matrix only. And with that, you can
yes.
compute it.
Yes, exactly.
Okay,
yeah, because as I
you.
said, yes, I said this. I mean, in the way we did the numerics, it might seem that we used the eigenvectors because we kind of explicitly constructed the thermofield level, and that you might think that you need the eigenvectors, but actually, as I said, everything at the end of the day depends only on the survival amplitude, and the survival amplitude is the spectral form factor, which only depends on the spectrum. So yes, it only depends on the spectrum.
Okay, thank you.
If you want to access information about the eigenstates, you could start with different initial states, not with the thermofield level, and then you would this would depend also on the structure of eigenstates, but we didn't explore that. So I'm a little bit out of time. Do I have 5 minutes or 10 minutes? Or but if you want, I can also stop here. I mean,
absolutely, yeah, no, 10 minutes is good.
Okay, yeah, 10 minutes is perfect. Yeah. Okay, so thank you. So we now try to approach this problem analytically. Okay, so all the calculations until now were done numerically. The usual approach. So and to do that, we are going to see how this suggests a new approach to random matrix theory. So the usual approach to, let me first review what is the usual approach to random matrix theory. It works as follows. One typically defines a random matrix theory through a potential of this form that controls the probability weight that one assigns to a given matrix. Okay. The conventional approach then goes by diagonalizing the matrix because, since the potential is constructed out of traces, it's good to choose another basis, which is the basis of eigenvalues. And then if we follow the probability distribution through that change of basis, we are led to the famous joint probability distribution for the eigenvalues, this probability distribution here. Starting from this joint probability distribution and with somewhat very sophisticated techniques, one can then compute the statistics of the density of states and of a number of the statistics of the density of states and the partition function, which is basically done by computing correlation functions of this sort, of endpoint correlation functions of the density of states or endpoint correlation functions of the partition functions. This would be the Wigner story. Now, the Cornelius story, for time-dependent scenarios, we have been discussing goes by choosing an initial state that could be, for example, a random state, running the algorithm and arriving at the tridiagonal form of the Hamiltonian, that we have done previously in a numerical manner. So, so if we started, so if we do this as we did for the Gaussian unitary ensemble, but in general, if we start with a random matrix, this tridiagonal form is going to be a random tridiagonal matrix. The problem is then to find the statistics of the Lanczos coefficients, namely the joint probability distribution of the Lanczos coefficients and generic correlation functions of the Lanczos coefficients. Is this clear? Maybe let me repeat it just so that it's clear. So in the conventional approach, one diagonalizes the matrix, and one seeks to find the probability distribution for the eigenvalues in this diagonal version, and statistics that one can extract out of it. For example, statistics about the density of eigenvalues, or equivalently, statistics about partition functions. But the Cornelius story to study time-dependent scenarios motivates another change of basis, which is a change of basis to a tridiagonal form. This tridiagonal form is again a random matrix, and the coefficients are random, and we need to find the joint probability distribution and their correlation. Okay. So the joint probability distribution turns out to be given by this formula here. It is derived in our article. The simplest path to this formula. So we use 3 different arguments, but the simplest one is it just uses one exact result. It is a seminal result derived by Dumitriu and Edelman in 2002 in their seminal article, that they found the exact they didn't locate it they didn't contextualize it in the Lanczos story. They just found that basically a random matrix, an ensemble of random matrix of tridiagonal random matrices with these statistics, where n are Gaussian probabilities, and these chi's are the chi's distribution. So if you take this ensemble and compute the joint probability distribution, then you find the generalized Gaussian beta ensembles. So now we can connect the result with the Lanczos approach, and then find the joint probability distribution for the Gaussian case, and then extend that measure for generic potentials, which is basically trivial because the measure doesn't depend on the potential in the same way as this measure here, the Van der Monde measure, doesn't depend on the potential that I put here. If I found it for the Gaussian case, I found it for any case. So so here I can find it directly. This basically this measure, this part of the probability distribution is like it plays the role of the I mean, it is like the non-trivial part, like the Van der Monde determinant, and this can be found from this exact result, and then extended to from this exact result concerning Gaussian matrices, and then extended to generic potentials. So now, having the joint probability distribution, we now follow the usual steps that a physicist would follow. So we start by taking the logarithm to obtain an effective action of this sort. In this effective action, we need to compute the trace of the difficult part is that we need to compute the trace of powers of the Hamiltonian appearing in the potential, but in the tridiagonal form, so that in the tridiagonal or Hessenberg form, so that the Lanczos coefficients appear. I cannot take the trace in the diagonal form. This is kind of involved, and doing this and taking the thermodynamic limit is somewhat technical. The end result is this formula here. Or better, this formula here, which is an action for the Lanczos coefficient, similar to the famous action for the density of states in random matrix theory. So in this term, so this would be the action for the actual Lanczos coefficients. In the thermodynamic limit, it is better to write everything in terms of this continuous parameter x, which is defined to be the Lanczos label little n divided by the Hilbert space dimension. And if we do that, we get a continuous, an action depending on two continuous fields, no, B of x and A of x, which is the final version of the action. Are there some questions? So this is, the technical, what is technically behind this, it's a little bit technical, But conceptually, I want to remark that it's very similar. So the approach is very similar to the conventional approach. So in the conventional approach, we take this joint probability distribution, then we take the continuous. We basically put this in the exponent, and we take the continuous thermodynamic limit, in which we write everything in terms of the density of states, and we get an action for the density of states. From where we can compute the saddle point equations and the 2-point function, for example. Here is the same. We have just that we trade the density of states by the Lanczos coefficients, A of x and B of x, and we get a different action, of course, because we are looking at different properties. Okay, so the saddle point equations for the Lanczos coefficients are then these ones. One can derive them. And by expanding the saddle point equations around the average, we can compute the 2-point functions, the covariances of the Lanczos coefficients. This is again quite involved. It is describing, I mean, it's developed in detail in the article, but I'm not going to go over it now. But what is important is that we can compare the solution to these equations for different potentials, namely the average Lanczos coefficients, and also their variance with numerical results. And this is done in this plot here. The upper part, so these three plots here are the average Lanczos coefficients. Well, the actual Lanczos coefficients of random matrices with different potential. This is a Gaussian potential. This is the Gaussian that we saw before. This is a quartic potential, and this is a 6-tick potential with also odd terms in the potential, not only even. These are the blues are the B's, and the orange are the A's. And in the middle, I don't know if you can see, but in the middle there is the prediction from the saddle point equation, which fits perfectly against the exact numerical evaluation. And the same for the covariances, so we can compute the covariances. So basically the fluctuations that you see here are on the average. These are blown up here. And again, the line in the middle is the analytical prediction that follows from the covariance. I mean, from basically from expanding these equations to second order. Okay, so sorry for taking more time. Yeah, I end with the discussion here. Thank you very much.
Thank you so much, Javier, for the wonderful talk. We had plenty of questions during the talk, but are there any other questions?
Maybe I can ask again just to make it. So this idea of for example, entropy saturation, a long time growth of the complexity, all that is just then a property of the spectrum, you're saying?
Yes. What is interesting is another way. So we are basically what is interesting about this proposal, which is somewhat arbitrary, as we were discussing at the beginning with this minimization. What is interesting is that this proposal is computable, is very explicit. And actually, it relates to, I mean, one can relate it to fine-grained physical properties, because it depends really on fine-grained physical properties, like fine-grained properties of the spectrum, but still is a function of the spectrum in the physical scenarios of interest, such as the thermofield double.
And it has the same property that it keeps growing after the entanglement saturates, so it keeps growing for exponential time. So okay.
Exactly. Yeah. That is that. So maybe I didn't explain myself very clear, but
no, I just want to make sure I understood.
Yeah. It's you can see here. So here everything is of order 1, as I was saying, but both the complexity in the y-axis and the time in the x-axis they are normalized by the dimension of the Hilbert space. So basically, everything that you see here is linear growth for times that are exponential in the entropy, and saturation at times that are exponential in the entropy. So this notion verifies the generic expectations. But it is interesting that it also tells you something about, let's say, so that those are kind of coarse-grained expectations. No, everything is on order of magnitude, is e to the s. So basically, saturation is on order e to the s. But we are saying something also about the prefactors. So there is this funny dynamics before the saturation, and is related to the universality of quantum chaos. To spectral rigidity and and the different universality classes of random matrix theory.
Thank you. That's a very nice talk. Yeah.
Any other questions for Javier? If not, let's thank Javier once again.
Thank you.
Thank you so much, and sorry for I missed the first few minutes of it.
Don't worry. Thank
Do
you.
you mind
Thank
if
you.
we
Very
post-
nice talk. Yeah.
Do you mind if I post the video on YouTube?
No, it's fine.
Okay, thanks so much, Javier.
We see Nima on at Princeton this
Yes.